Hello. All right, I'm going to try this. I am having internet connection problems. There may be some buffering or it may just cut out entirely. I'm going to try to keep an eye on the bit rate so that if it drops too low, I know we'll just give up and do it another time. Seems okay at the moment, but let me know if you're having a lot of trouble with it, and I'll try to pause and then come back. I think the evenings are just tough because everybody's on the internet in the evenings. But at the moment, it seems maybe okay. So anyway, I hope you had a nice weekend. And today we're going to talk about chemical compounds, and we're going to learn about how atoms combine to make compounds and different ways they do that. And then we're going to talk about how we name those compounds, how we refer to those compounds. And that part in particular is sometimes gives people some trouble. So we'll spend a little extra time on that when we get there. All right. So we talked about the periodic table last week. So you should be able to do this now, indicate where metals and non-metals are on the periodic table here. So here we got metals. We're on this side. Non-metals over there. And then right in the middle, we have the metalloids or the semi-metals. So kind of in between. All right. So our first distinction that we need to worry about is the difference between covalent compounds and ionic compounds. Now, later in the class, we're going to get more into what precisely that means. But for now, let's just define these a little bit. So there are two different types of bonding. Oops, sorry. You might guess ionic has to do with ions. So you've got charged particles, plus and minus, attracting each other. And covalent are atoms connecting in a different way where they share their electrons, and we'll get into more about the details of that later. So let's just look at these three samples here. We've got methane, CH4, dinitrogen trioxide, N2O3, and sulfur difluoride, SF2. So for methane here, let's name the elements. So we look at the formula. If that's too small here, I can make it a little bigger. So we look at the formula, we see CH4, and we know that that is carbon and hydrogen. Now, just a note, you don't have to have that memorized. You'll have a periodic table. You can look it up on the periodic table. Are they metals or non-metals? Well, we can look at the periodic table to see where they are, and you'll find that carbon is over here, and hydrogen is over here. But we got to be careful here. Hydrogen is kind of an exception. Hydrogen is not really a metal. I think we looked at that last time. So these are non-metals. And then you can do the same thing for the rest of them, and you should be able to come up with a particular generalization that if all of these are covalent compounds, how can you tell a covalent compound? And I'll let you come up with that. So then you can, let's contrast that here with ionic compounds. These are some ionic compounds, and you can see they look quite different. Rather than being in discrete units like this, they have this more like packed ball type structure where there's just a bunch of balls all packed together in a cube. It doesn't have to be a cube necessarily, but in these examples it is. So in this time, when we look at the different elements that are in there, our formula is, like for this first one, our formula is BaO, barium oxide. But that doesn't mean, according to this picture, that there's just one barium and one oxygen. There's actually a bunch. So maybe there's something else going on. It has something to do with a ratio. And so these are some ionic compounds. And one thing that you'll see, I guess I'll just tell you so we can go on. Covalent compounds, for what we will see, are primarily all made from nonmetals. So when you see all the elements over on the right, nonmetals, it's probably a covalent compound. Whereas ionic compounds generally tend to be a metal and a nonmetal. You can see barium and oxide, potassium and fluoride, sodium and chloride. Right, so one element from one side, from the left, and one element from the right. Now that's not a 100% always rule. That's a generalization that can sometimes help us. But we're going to see some examples where that doesn't quite fit also. So it's not like an absolute rule. It's more like a this usually works kind of a thing. All right. So we talked about cations and anions, positively charged ions, negatively charged ions. And what type of compound is comprised of them? Well, that would be ionic, right? An ionic compound has positive and negatively charged ions attracted together. So all this stuff you can go through. This is just helping you distinguish ionic from covalent. But basically what I just said is all you need. If you've got a metal and a nonmetal, it's ionic. If you've got two nonmetals, it's covalent, with some exceptions that we will see later. All right. So you can see in a picture like this how that is different at the molecular level or at the atomic level. A covalent compound like in B here is going to be made of discrete units that we call molecules. So these are each a separate molecule, and they might be slightly attracting the other ones, but they're not chemically bonding with the other ones. Whereas here we have ions that aren't really connected in the same way. You can see the spheres, they're still kind of discrete spheres rather than being kind of mushed on top of each other. And so they generally, the cations and the anions will have some sort of an alternating structure. It doesn't always have to be exactly a square cubic alternating structure like this, but something like that, because we know that positive and negative attract. Okay, so to start building these compounds, before we get into all this mess, sorry, I went too far. Okay. Let's just talk about another thing that we mentioned last time, but it becomes a lot more important now. Elements in the same group, that is the column of the periodic table, tend to have the same charge. So all the elements in group 1 tend to make a +1 ion. That means they lose an electron. They make a +1 ion. All the elements in group 2 make a +2 ion. Over here, in group 13, they make a +3. Sometimes a +4 in group 4, but that's not always, we don't see that a whole lot. Or we do see that, but there's other options as well, we should say. And then we've got -3, -2, and -1. And the noble gases way over here on the right don't make ions. So from that, then, we can start thinking about how to put these compounds, how to put ionic compounds together. And we're going to start with ionic compounds and then get into covalent compounds later. So before we get into all the naming stuff, I want to where am I going here? Sorry, I got lost in the scrolling. All right. So before we get into the naming, I want to practice just how we put these compounds together because we know the charges, or we can get the charges from the periodic table. So let me show you how that works. Let's say we have sodium oxide. Now we can probably figure out what this formula should be without even really knowing the naming rules yet. So what we want to do first is look up each element on the periodic table, see if we can find it, and then guess what the charge would be for each of those ions. So we'll start with sodium. We'll pull up our periodic table. If you have one that's easier to see than this one behind me, use that. But you can see sodium is way over on the far left in group 1. It is symbol is Na, and because it's in group 1, we can predict that it's going to make a +1 ion. So we can write Na with a plus because we know this is an ionic compound, metal and nonmetal, and we know that sodium makes +1 ions. So there is a neutral sodium metal, but in an ionic compound, we're always going to have the ions. And so we know sodium has to make +1, so we do that. All right, so then the next word is oxide. Now, if you look at the periodic table, there is no oxide anywhere on here. That is not one of the elements, but there's an element very similar to it that you could probably guess what it is, and that is oxygen right up here. So it turns out one of the naming rules is that the anions get the end of their name cut off, and it says, and you say "ide," IDE instead. But we could probably figure it out without even knowing that rule, right? Just because it's it kind of seems like maybe oxygen, or at least it seems more like oxygen than anything else. So we can put an O there. But remember, this is an ionic compound, so it's not enough to just say O. We need to know what is the charge of this anion. So we go back to the periodic table, and we say, okay, oxygen is in column 16. That is 2 from the end, and we know going over on this side, we've got 0, -1, -2. So oxygen being in this column right here tells us that its charge must be -2. And as we discussed before, you can either write that as -2 or 2-. I have always done it this way, so that's how I do it. But it's fine to write it -2 also. Okay, so those are our two ions that are involved in this compound. And we figured that out just from those names and looking at the periodic table and knowing something about which elements form which ions. Now, just so you know, so you're not too worried, this whole middle section where we don't have predictable charges like that, we're not going to be able to do that exactly. This only works for elements where they always make the same charges, so the far left and the far right of the periodic table. So if we want to make a formula, a chemical formula for sodium oxide, we've got the Na and we've got the O, but we can't just squish them together and say that it's NaO. And the reason is that the compound, the ionic compound, must have a neutral overall charge. So if we said Na and O, we'd have +1 and -2, and that does not equal 0. So what we can do instead is we can add another sodium. Now, overall, we have 2+ between the two sodiums, and that matches up nicely with the 2- to make an overall neutral compound. And the way that we write that is with a subscript 2. So we say Na2O, and that is the correct formula for sodium oxide. The reason it has to be like, or what that is telling us then, is that every oxide ion needs 2 sodium ions. So rather than a molecular formula, which tells us exactly how many of each atom are in a discrete molecule, in an ionic formula, we just want to know the ratio. So for every 2 sodiums, there's always an oxide. For every 1 oxide, there's always 2 sodiums. All right, let's try another one. Calcium chloride. So we're going to do the exact same thing. We're going to look up calcium on the periodic table to find both its symbol and its charge if we can. And so I see calcium right over there in number 20, which is in column 2, group 2. And that makes it a +2 ion, and its symbol is Ca. And then chloride, well, once again, if we look at the periodic table, there is no chloride, but there is chlorine right here, which certainly seems pretty similar. And in fact, it is. So that symbol is Cl, and it's a -1 charge. So -1 like that. Okay, and now we have to do the same thing. We have to balance it out so that the ratio gives us an overall neutral charge. And to do that, we've got extra positive charge for the negative charge, so we got to add another one of these. Now we've got 2- overall, 2+ overall, so our formula is going to look like Ca+. Cl2. That's how ionic compounds work. So you have to balance the charges so that you have an overall neutral compound. Okay, and then let's do one that gets a little bit trickier. Aluminum oxide. So we'll do the same thing. Look at the periodic table. I can tell you that aluminum is Al, and its common ion is 3 plus cation. And oxide we already did, so we know that one's O2 minus. All right, so now we have to make a balanced compound of aluminum and oxide. And the reason this one's a little bit trickier is because you got a 3 and a 2. So if we just say, oh, we need more negative, let's put another oxide in there. That doesn't quite work because now we've got -4 and +3. So maybe we need another aluminum. Well, that doesn't work either because now we've got +6 and -4 overall. But if we then add one more oxygen or oxide, then we should have them balanced out. -6 plus 6 looks good. So that formula is Al2O3. So when you see those numbers that aren't as easy as just like when one of them is 1 and the other one is 2 or 3, and you can just keep adding more of the 1, you may have to actually change the numbers of both of them to get a ratio that gives you the correct overall charges. All right, so now let's talk about naming these things. So what if we wanted to go the other way? What if I gave you a formula like some of these over here, KBr, Al2O3, CaCO3, whatever, and I wanted to know what is the name of that. And this is a little tough. It's going to take some practice, but it's really, really important because it's how we communicate this information. Some people say, learning different subjects is kind of like learning different languages, even if the subjects are not technically different languages. But that's true. We have to know what each other are talking about to move forward and to be able to do more interesting chemical stuff. And part of that is knowing how we name our compounds, so that when I say, hey, go grab some calcium chloride, and all the chemicals are labeled with just their symbols, you know which one's which, and so on. So this is kind of the overall picture, and I know this is quite daunting, but it's just here for reference, and we're not going to use this until after we're done with going through the naming rules. This is kind of the overall summary of everything. So right here is an important that a lot of people skip and causes problems. So let's put a little star there because this is the part that's really not difficult. The most important first step to naming compounds is to decide if a chemical is ionic or covalent. And how do we decide that? We already talked about it. Ionic compounds are going to be made of ions, and covalent compounds, nonmetals. And it looks like I have internet issues again. I'm going to pause for a second, see if it catches up. All right, well, I think I've got some here. Oh, there it goes again. Okay, well, let's talk about covalent compounds at least, and that'll give us a good start on this stuff, and then we'll get into the rest of it on Wednesday. So when we decide that a particular compound is covalent, by noticing that it is entirely made of nonmetals and just 2 of them. All right, these are binary covalent compounds. So if you see a bunch of different elements, something else is still going on. But if we just have 2 elements and they're both nonmetals, then we can use this system to name it. It's the easiest type of naming that we've got. And all you do is, let me zoom in on this so you can see it, is you simply say both elements which with a prefix that tells you how many there are. So for example, P2O5, we notice those are both nonmetals. So this is a binary covalent compound. And there's 2 phosphorus and 5 oxygen. So the prefix for phosphorus is, or for 2 is di. And the prefix for 5 is pent, or sometimes penta. And so we've got diphosphorus pentoxide. The only other thing to worry about then is what we've kind of already encountered a little bit, that we're going to drop the end off the second element and say "ide." Now there's a little review chart here of how you can come up with these different prefixes. And one way to remember them is to think about your geometry and how you named these different types of shapes. So if you've got a tetrahedron, then you've got tetra is your prefix for four of a particular atom. If you had a 5, then that's a pentagon, so then it would be penta, and so on. And if you don't remember those, that's fine. You can look them up. We're not going to see any more than 10. So let's practice this. Just a couple quick exceptions. The prefix for only 1 is mono. But if the first element only has 1, since that's really common, we drop that prefix. So for example, OCl2, we've got 1 oxygen and 2 chlorides. We don't call it monooxygen dichloride. We call it oxygen dichloride. Like that. So I'll let you take a shot at these. And then you should also be able to go the other direction. The nice thing about these types of names is because they tell you exactly how many are in the molecule, if you know the prefixes, they're pretty easy to write down. So sulfur dioxide means a sulfur and 2 oxygens. Dinitrogen tetroxide means 2 nitrogens and 4 oxygens. Good question. Is the ending only for covalent? No. We use those endings for ionic compounds as well. So if you had like in our examples up here, we had oxide and chloride also. So we're actually going to use that in pretty much everything. All right, and I'll leave a couple for you to do there as well. Okay, and then let's also, as long as things are maybe working, let's also look at the one type of ionic compound, the binary ionic compounds, with just one type of ion. And these are the ones that we just did before. So if you have, if we're going the other way now, and we want to name a compound, these are also pretty easy. In fact, they're kind of easier because you don't have to use any prefixes. That's the beauty of knowing the ions, is if a compound can only make one type of ion, then we don't really need to specify how many of them there are, because it's always going to be a particular number. So, for example, let's go down here and look at MgCl2. So we first have to identify that that is an ionic compound. It's a metal and a nonmetal. So we can't call this magnesium dichloride, because that type of a name is reserved for only purely covalent compounds. Now that we have a metal in here, we have to use the ionic naming rules instead. And so we've got all we have to do, assuming that these are only one type of ion, which means they are in one of these columns on the periodic table where they always make the same type of ion, then we just have to say their names. We say the metal, and then we say the nonmetal with "ide." So let's just confirm magnesium is indeed over there in the column 2. So we can call this simply magnesium chloride. And the reason that works is that everybody knows magnesium can only be +2 and chloride can only be -1. So if you have those two together, you're always going to have a 1-to-2 ratio. So there's no need to add any prefixes to tell people how many of each thing there is. This one we did earlier, we did the other direction. And then watch out down here, there's a little bit of a trick. I don't know if you noticed that, but that, even though it's in this list with these other ones, that is a covalent compound. Right? So the way this worksheet works is it kind of it introduces a new thing, but then tries to keep reinforcing the old thing as well. So there's plenty of good practice with this. Before everything crashes completely, I will stop here, and hopefully all the video makes it up to YouTube. But give this stuff a try. If you want to work a little bit forward, a little bit past in the packet, that would be great too, because then on Wednesday you can bring your questions, and I can answer, because I'm sure you'll have questions. Why does this name go like this? Why doesn't it go like this? Because it does get more complicated. So if you can, practice the stuff we did, but then also try to get on a little bit and see if you have some questions. If you'd rather just wait, that's okay too. So question from YouTube here, from Breeze. On group line 14, we see ±4. Does this mean it can act as a positive or negative? Yeah. So generally that's going to be, it's because that row kind of gets crossed by the metalloids here. So if you see, like, it's right here. So those are all going to act a little weird. Carbon can make a sort of a -4 ion. Silicon kind of. And then as you get down into the metals, they tend to only be +4, because metals, with few exceptions, metals make cations, positive ions. So that's really why it says plus or minus. There really isn't a carbon +4 ion, but there is a carbon -4 type of ion. So that's why. Generally, we won't see those as much, because even when we get down here, it's not super fixed. Like, you've got tin and lead here, but they can be +2 or +4. So that's a whole different thing that we'll get into later. But yeah, good question. All right, so give these a try, see how they go. It's easy to look up your answers here. I will, of course, give them to you if you want them, but you could always just look up the formula for calcium bromide on the internet. I'm sure it would come up. I hope it would come up properly anyway. But please try it first and really give it a shot and see if you can both get the name from the compound and get the compound or the molecular formula or the ionic formula from the name. If you can do both those things, then you're good. And then we can start moving on into these slightly more complicated naming rules before we put the whole thing together and you can just name everything. That's ultimately the goal, and I think you can do it. So yeah, any other questions before we call it for right now? All right, well, hopefully the video made it in there okay. And whatever we need to review on Wednesday, we can do it then. So I'll see you Wednesday. Good night, everybody.